So here I will be explaining how to solve propped cantilever beams using consistent deformation method. So this is the first topic in unit 3. So I will just start writing here. So in unit 3, the first topic will be consistent deformation method. And here you can solve two types of problems. One is propped cantilever beams, and one more is fixed beams. We will first see analysis of propped cantilever beams. So propped cantilever beam is a cantilever beam which can have a support at the free end, like a roller support, or you can have a simple support, or you can have support like this. So this we call as propped cantilever beam. So here, if you see, if I consider the beam to be axially rigid, I will have one vertical reaction here, one moment here, and another vertical reaction here, which is usually called as prop. Okay. So here, my total number of unknowns are 3, whereas available equations are only 2. That is summation v and summation m equal to 0. So I will have one extra unknown which cannot be determined using equilibrium equations. So to find this extra unknown, I will require something called compatibility equation. Okay. So you have to remember here in propped cantilever beams, if I'm considering them to be axially rigid, you will have 3 unknowns, but 2 available equations. So there is one extra unknown. So you have to formulate one extra equation to solve the problems. Okay. So now here, the compatibility equation is developed by considering the deflection due to loads and deflection due to draw as the total settlement of the supports. Okay. And from moment area method, deflection can be calculated by taking area of bending moment diagram divided by EI multiplied by the centroidal distance. Okay. So this equation will be used in analysis of propped cantilever beams, which is an extension of moment area method. And delta is nothing but settlement of supports settlement of supports that can be either sinking or rising of supports. If there is no settlement given in the problem, then you can consider delta as 0. Okay. So, and in propped cantilever beams, you will be asked to analyze the beam and then to draw SFD, BMD, and elastic curve. So they will ask you to analyze the beam, and once you analyze, you will be finding the member end moments, and you'll be finding the support reactions, using which you can write the shear force diagram, bending moment diagram, and the elastic curve. So I will take one example now, a simple example, and try to solve a propped cantilever beam. So let me take as example 1. So I will take a propped cantilever beam with one end fixed, one end is supported by a roller support, and there is a central point load of 60 kilonewtons, and the complete span is 6 meters. We take the ends at point A, point B, and point C. Okay. So here they have asked the question as analyze the prop cantilever shown using constant deformation method, and also draw SFD, BMD, and elastic curve. Okay. So here the first step will be you have to draw the bending moment diagram for the prop cantilever beam. So I can divide this beam into two simpler beams. That is, one is cantilever beam with point load of 60 kilonewtons, 3 meters, 3 meters. This is point A, this is point B, this is point C. And another beam will be a cantilever beam with prop. So I know, because I have a roller support at point B, there will be one reaction here, which I will call as RB, and this is called as the prop. Okay. So I have here point A, point B, C. This is 3 meters. This is 3 meters. Okay. So now, once you have divided the beam into simpler beams, you will have to draw the bending moment diagram. So I know I have a cantilever with central point load. So I will get a Hawking bending moment diagram like this. This will be Hawking bending moment, and the bending moment value here will be 60 into 3, that is 180 kilonewton meter, and this point is A, this point is B, this point is C, this is 3 meters, this is 3 meters. And similarly, for this beam, I will get a sagging bending moment diagram like this, and I will take this prop as RB, and the moment here will be RP multiplied by 6. This will be my sagging bending. Okay. So once you draw the bending moment diagram, you can apply your consistent deformation equation, that is delta due to
I can learn to understand you.
loads plus delta due to prop is equal to settlement of supports. And here there is no settlement of supports given, so you can take this value as 0. And you know delta can be calculated using Morse theorem, that is area of BMD divided by EI multiplied by X. Okay. So now here the centroidal distance X bar, you have to take from centroid to the prop. This is one of the principles used in consistent deformation method. So now if I apply this equation, I have two bending moment diagrams here. So I have to apply to both the bending moment diagrams. So if I apply to the first bending moment diagram, it is a hogging bending moment. So I can say here it is minus half into base into height is 180, that is area of BMD divided by EI. If nothing is mentioned about EI, you can take EI as constant. This is multiplied by X bar. So now X bar for first BMD will be from the centroid till the prop. This is your X bar. So the X bar will be 2/3 of 3 plus 3 meters. This is for the first BMD. And the second BMD is a sagging BMD. So you can write it as plus area of BMD is half base is 6 meters, height is 6 times RB, 6 RB divided by EI multiplied by the centroidal distance. The centroidal distance for the second BMD will be from the centroid till the prop. So this is my X bar, and that is equal to 2/3 of 6. This is equal to 0 because there is no sinking of supports or rising of supports. So you can take delta as 0. Now if I simplify this equation, I will get minus 1350 divided by EI plus 72, 72 RB divided by EI is equal to 0. I can take 1 by EI as a common factor and send it to right hand side, which will become 0. And here the only unknown is RB. So if I solve for RB, I will get my reaction at B as 18.75 kilonewtons. Okay. So now I know RB is equal to 18.75 kilonewtons. So once you know RB, you have your propped cantilever and you have RB here, 18.75 kilonewtons. There is a point load here, 60 kilonewtons. This is 3 meters, 3 meters A, B, C. So now because I have a fixed support here, I will have a vertical reaction, which I will call as RA. And I also know that RB is 18.75 kilonewtons. So I can apply my static equilibrium equation, that is summation V equal to 0. And the sign convention here is all upward forces are positive and downward forces are negative. So if I apply this equation, I will get RA plus RB is equal to 60. So I know RB is 18.75. So RA will be 60 minus 18.75. So I know RA is equal to, I will get it as 41.25 kilonewtons. So this is RA. So I know RA is 41.25 kilonewtons. So once you know RA and RB, you can draw the shear force diagram. And to draw bending moment diagram, you have to calculate moments at various points in the structure. So I know B is an end support. So the moment is going to be 0 there. So I can write here calculation of bending moments. So I know bending moment at B is equal to 0. And bending moment at C, I will consider right hand side. And I will take sagging bending moment as positive. So here I have a reaction RB and I'm taking moment about this point. So RB causes an anti-clockwise moment on the right side. So it causes sagging bending moment. So I can write it as RB, that is 18.75 into 3, and this value will be 56.25 kilonewton meter. And similarly, bending moment at A can be calculated. I will consider right hand side. So here I have reaction at B and 6 meters. This is anti-clockwise. So right side anti-clockwise will give me sagging bending moment. So I can write it as 18.75 into 6. And I have 60 into 3, which is clockwise. So right side clockwise will give me hogging moment. So it will be minus 60 into 3. So if I simplify this, I will get the moment as minus 67.5 kilonewton meter. So I get a negative sign here, which means it is a hogging bending moment at support A. So now I can draw my shear force diagram. So the units for shear force diagram is kilonewtons. So I have my reference. This is point A, this is point B, this is point C. So at A, I have upward force of 41.25. So I have to represent this by drawing a line upwards, 41.25. And from point A to point C, there is no load. So it is going to be uniform. And at point C, I have a downward force of 60 kilonewtons. So 41.25 minus 60 will give me minus 18.75. And from point C to point B, there is no load. So it is going to be uniform. And at point B, I have an upward force of 18.75. So minus 18.75 plus 18.75 will give me 0. So this is positive region and this is negative region. So this is about shear force diagram. The sign convention I have used is I have drawn from left to right, and all upward forces are positive and downward forces are negative. Next, I draw bending moment diagram, and the units will be kilonewton meters. So I have point A, point B, point C. I know bending moment at B. Sorry, this is point B. This is point B. This is point C. This is point B. This is point C. So I know bending moment at point B is 0. So this is the point. Bending moment at C is 56.25. That is positive. So I have to show it above the reference, 56.25. And bending moment at A is minus 67.5 kilonewton meter. So that will be in negative region. So I'll show it here, 67.5. Okay. And there is only point load acting on the midbutt. So I can join all these points using a straight line. Right. This is the positive region. This is the negative region. Okay. And here, wherever the bending moment is changing its sign, I call it as point of contraflexure. You can calculate point of contraflexure using these two similar triangles. Okay. You can take this distance as x. So this distance will be 3 minus x. So using similar triangles, you can write x divided by 67.5 is equal to 3 minus x divided by 56.25. So you will get x as so this will be, if I simplify this, x into 56.25 is equal to 3 minus x multiplied by 67.5. Solve for x. Anyway, you can calculate the value of x from here. So that is the distance of point of contraflexion from point A. So this is about drawing bending moment diagram. Then the next will be drawing elastic curve. So for elastic curve, you will have to first have bending moment diagram. Once you have drawn bending moment diagram, you draw the given beam without showing the loading. You know this is point A, this is point C, and this is point B. So point A up to this point of contour flexure, you have a negative bending moment. So that means it is hogging bending moment. So for this entire region, your structure has to hog, the beam has to hog. So I show the hogging like this. And from point of contour flexure till the support B, I have sagging bending moment. That means the beam has to sag. So I can draw it like this. This is my point of contour flexure. Okay. So elastic curve has to be drawn by seeing the bending moment diagram. For the hogging region of bending moment diagram, you show the beam as hogging, and for sagging region of the beam, you show it as a sagging curve. That will give you the elastic curve. Okay, so this is the solution for the first problem, which I have solved in the course material. You can go through this and get back to me in case of any doubts. I'll be solving the remaining problems also shortly and sending the video links so you can just go through it and solve the remaining problems.